So we're going to wrap up priority queues today and then move on to our next topic, which is going to be hashing, which will let us introduce some more basic techniques that we'll be using throughout the course. If you recall, last time we looked at the DiNardo and Fox priority queue. And this was basically a, how would I say this? Compressed, no, that's not a good word for it. An incomplete trie. So basically, we know what a trie data structure is. It has nodes that are made up of a collection of siblings, and a given node points to its children, which are again represented as an array. We have some number delta of these sibling arrays. Sorry, some number delta of children of a particular node. And we have some depth k, and this means that we can store a total of delta to the k values in the trie. But for performance, DiNardo and Fox recognize that in our application to shortest paths, we don't need the whole trie at once. And so they only materialize one sibling array per level of the trie, which means that our space is very small. And they do lazy pushdowns of items. Basically, you only push an item down when it's in the minimum bucket on a given level. So you expand the minimum bucket on each level. And that means that you know where the minimum item is because it's going to be in the bottom level because it was always in the minimum bucket. But a lot of other stuff just hangs around at higher levels until you get to it. And we used this lazy procedure of when you want to delete the minimum and find the next min, you scan along the bottom block, you check if there's anything left in the bottom block. If there is, you scan in order to find it. Otherwise, you go up the array, the levels, looking for a non-empty block. Once you find a non-empty block, you scan from where you are to the next non-empty element, the next non-empty entry in that block. And then you expand that entry down, unpacking the items in that bucket into lower and lower levels until the new minimum item ends up in the new minimum block, in the new bottom block. And what we argued last time was that the amortized cost, after you insert an item, it just gets pushed farther and farther down the data structure. So the total amount of work you're going to be spending on that item is only the k work that you spend moving it down from level to level. We argued that this doesn't even change if you allow delete min, because when you do delete min, when you do decrease key, because a decrease key simply involves moving an item to a smaller entry. And so you might, as a result, move it into the minimum bucket on a certain level and need to push it down, but that is still covered by the assumed cost of pushing the item down to the bottom of the trie. So insert and decrease key together only cost order k per item. And then there's delete min, where we argued that the scan cost is at most k, and the descent cost, the scan cost is about delta, and the descent cost is at most k. And therefore, this entire sort of the going up to find a non-empty bucket is upper bounded by the cost of pushing the new minimum item down. And so that means that overall, the cost of doing a delete min is only the cost of that one scan, because the pushdowns have already been paid for. So we get a delete min cost of delta, a decreased key cost, and an insert cost of k, an insert cost of k and decreased cost of 1, and we ended up with a very, very fast order m plus log c over log c times n runtime for doing shortest paths. So I raced through that because that was just our background. But do people have any questions that lingered from the last lecture? Because if not, I will continue on from there.
Quick question. I think that the notes aren't actually, I can't access them on the class website. Not sure if that's like a bug on.
The notes just for this particular lecture or for any of the lectures?
Just for the bucketing lecture.
Okay, yeah, those might not have been inserted properly into NB. I'll make sure that the TAs take care of that. Actually, if you could do it during class, that will be fun. That would be great, because that way people can find it afterwards. All right.
Actually, David, just click on the one for the next class. Like, it should be, yeah, I think they're like off by 1 or something, and there's one in the middle that doesn't work. But I think there are notes that covered yesterday's lecture.
Okay, got it.
Yeah, you just have to play around with the URL. I can put it in the chat.
Great, thank you, everybody. All right, so moving on. We've got this m plus log c over log c. It's not quite that good. And I want to point out that, when you're working in the world of data structures, the log n or log c is kind of this natural parameter, right? We spent a lot of time looking at minimum spanning trees where we were trying to get from m log n to m plus n log n, and then to sort of squeeze away that log factor. In data structures, you're generally counting things in terms of logs. You can't do anything about the linear term, and it's really about that additional logarithmic factor. So in follow-on work to DiNardo and Fox, Cherkassky, Goldberg, and Silverstein had or applied another insight. And this is what I brought up at the beginning of, at the end of last lecture. If we think about this up, over, and down that we need to do in order to find the next min, I mean, up and down are very straightforward, but the moving over, the scanning for the next item, is simply a particular way to find the smallest non-empty bucket in a particular level, which is what we have to do in order to know where to unpack things. But what is this problem of tracking and finding the smallest non-empty bucket in an array of entries? Well, that's a min finding problem, right? Each of these entries is associated with some number, and we want to find the smallest number that has a non-empty bucket. So if we imagine having a collection of the non-empty buckets by number, we want to find the smallest number in the collection. And of course, that's a priority queue problem, right? We sometimes create a new non-empty bucket, we sometimes empty a bucket, so we have to put things in and out of that priority queue. We need to insert and delete, and we also need to be able to find the minimum of that priority queue and delete it. So we're doing that by scanning, which seems pretty foolish given all of the fancy data structures for priority queues. So Cherkassky, Goldberg, and Silverstein said, well, why don't we just take the DiNardo and Fox priority queue, but add a standard heap to find the minimum the minimum entry at the top level. Okay, so essentially what they do is they take this Denardo and Fox data structure with its many layers of relatively small buckets, and they say, well, why don't we make the top layer much, much bigger? We'll keep the other layers the same. But now for finding the minimum bucket in this big upper layer, we will stick on a standard heap. Okay, so even if the upper layer is quite large, doing a delete min and insert and delete there is still going to be pretty fast, right? If you think about it, we already know that we're going to be spending kind of K or delta work for each operation. So that suggests that if we just make the heap size like, 2 to the K or 2 to the delta or something, then the logarithmic cost of interacting with that heap is going to be negligible compared to the other work of the data structure. But what's the advantage? Well, the advantage is that since the top layer is so much larger, we don't need as many layers in order to have a range of C, right? Remember that we need a range of C for our values, but we can now get that with fewer layers of blocks. And they showed that with this small and simple change, they were actually able to improve the runtime to order m plus n times log C to the 1/3 power. So again, this may seem like a minor change, but in the data structures world, it's a big change. You've gone from log C to the 1/3. So again, the comparison for sequential algorithms would be going from an n³ algorithm to an n algorithm. It's a significant improvement. Now, there's not any tremendous new theory here, but I wanted to flag this paper for a couple of reasons. One is to point at this fellow Goldberg. Andrew Goldberg is one of the people I really respect for his work on experimental algorithms. And so foreshadowing the project that you're going to be doing at the end of this class, one of the things that algorithmicists do after they prove theorems is they implement algorithms and they see how well they work in practice. And there's a science to this, right? It's not just a matter of implementing an algorithm. You can be very sophisticated in how you test and evaluate the algorithm, thinking about what kinds of inputs are going to make the algorithm really unhappy. How do you really make it work in the worst possible way so that you can argue what its performance is in practice? How do you measure that performance and sort of separate out sort of basic operation times from issues like caching? And also, what kind of heuristics might you introduce that could have significant benefits in improving the runtime in practice, even if you can't prove anything about them? So there is a whole line of work on experimental algorithms, and Goldberg is one of the real great people in that field. So if you ever want to do these kinds of algorithm implementation experiments, reading papers by Goldberg is a good way to get examples of how to do it well. Sometimes you even will get new theorems out of seeing how these algorithms perform in practice and developing hypotheses that you can then prove mathematically. Now, the other thing I thought I'd mention about this one is this third author, Silverstein. He was my brother's college roommate, and afterwards he joined me at graduate school at Stanford and ended up with my desk after I left. And he was a great guy. My dad really liked him. And so my dad was really sad when Craig dropped out of graduate school after a couple of years. And he sort of walked around, bemoaning this fact for years. Such a great guy, had such a bright future in front of him, but he just couldn't finish graduate school. But it worked out okay for him because the reason that he dropped out was to become the first employee at this little startup called Google. And so he had, I think, a good reason to leave graduate school. And he's since gone on to do really great work at Khan Academy as well. But it just shows you where algorithms can take you. So I wanted to mention that as well. Oh, and they called this a hot queue, which now stands for heap on top, as opposed to heap order tree. But I think they just called it that because it's a cute name. All right. So, sorry, was there a question?
Yeah, I have a question. Why can't we add heap to multiple layers?
That's a very good question. In fact, that's exactly what the question that I'm going to ask now. And I mean, that sort of is the natural progression when lecturing, but chronologically, this is backwards. So the Cherkassky, Goldberg, and Silver, the hot queues, they applied an insight which actually came from a much earlier algorithm, or a much earlier data structure known as the Van Emde Boas priority queue. From 1977. So this actually even came before Donardo and Fox, right? But it asked exactly the question that you're asking. It said, you know, if we're going to have some kind of queue data structure, right, with a top layer and a next layer, maybe many next layers, right, because we didn't have Donardo and Fox yet, right? But we're going to have these ranges of buckets which are going to descend downwards, and you know, we're going to use the ordering to track the minimum by walking down the minimum non-empty bucket at each layer. But Van Emde Boas is the one who really recognized that finding a non-empty bucket is a priority queue problem. And so we should just go all the way in on recursion, right? So, you know, we can put a priority queue on top of each of these layers in order to be able to more quickly find the non-empty bucket in a layer. And that gives us a better priority queue. But of course, if we have a better priority queue, that's the one that we should use on the layers as well. So to talk about Van Emde Boas, I'm going to slightly change my vocabulary. Instead of talking about the maximum integer value, I'm going to talk about B-bit words, and you'll see why in a minute. Okay, so this is basically saying that the value C that we want to work with is 2 to the B. All right. So the structure, so, you know, I usually like to give intuitions before diving in, but with the Van Emde Boas structure, it really helps to have the explicit definition of everything to start with and then talk about it afterwards. So a Van Emde Boas priority queue on B bits, which I will call Q. Q is a, so it stores the minimum value in the entire queue. Okay, it actually sets it aside. And oddly enough, this is a critical idea in the Van Emde Boas queue. Right? You know, we've talked before about how you can always keep your finger on the minimum, but here it's actually critical that the minimum not be in the rest of the data structure. It also includes an array, which I will call q.low. And this is going to have, sorry, let me improve my notation. This array is going to be of size square root of C. Okay, and the reason for that is that it is if you think about it, this contains b over 2. Each of these indexes has b over 2 bits. That's why we end up with square root of c. And q dot low, each entry in this array is a Van Emde Boas q on the square root of c values in the relevant range. Okay, so we take the entire range of size c and we break it up into square root of c range, square root of c subblocks of size square root of c. And on each of those subblocks, we generate another Van Emde Boas priority queue, and we point at it from this q.low array. Does that make sense? All right. We also have an array, or sorry, not an array. We also have another Van Emde Boas queue, which I will denote by q.high, of non-empty blocks. Right, so we've got these root C blocks in the q.low array, and we keep track of which of those blocks is non-empty in the q.high array. So notice that q.high is storing up to root C block numbers, and each of them is going to have b over 2 bits because there are square root of c of them. Okay? So in one sense, the Van Emde Boas queue is just a 2-layer trie, right? Where we have a top layer of width root c, and it subdivides into root c different blocks, which are also of size root c.
What is q.high exactly?
Q.high is a Van Emde Boas queue, right? So Q.high is storing the indexes of the non-empty level 2 blocks. Did I answer the question?
Yep.
Great. So again, this is going after exactly what we discussed, right? Finding the smallest non-empty block at the top layer is a priority queue problem, right? We may create a new non-empty block when we insert something. We may create an empty block when we delete something, and we often need to find the first non-empty block. So we should use a priority queue for that, and that's what q.high is doing. All right, let's talk about how to do the basic operations now. Let's see if I can scroll these blackboards. All right, so how do we insert an item X into our Van Emde Boas queue? Well, what's the first kind of special case we need to think about? One possibility is that X is actually the new minimum. So if X is less than the queue's minimum, then we should swap them. All right, so we should put X into q.min, and now imagine that we're inserting the old min as X, right? Now we have to put X into the recursive structures. Right? So what does that mean? Well, let's expand so that we can think about the two layers separately. X as two pieces, X high and X low. These are the B/2 high bits. And these are the B/2 low bits of X. Okay. So now that I've defined these quantities, how do I proceed to update the various levels and their data structures? What do I need to check first?
I guess if the high bits like correspond to an empty block or a non-empty block.
Right. So I need to think about whether the second level block is empty or not. Right. I need to check if Q dot low indexed by the high bits. In other words, I need to check the second layer block that X belongs in. If it's non-empty, right? If there's already items and already a recursive priority queue there, then I just need to insert XL into Q dot low of XH, right? Let me get rid of check and just say, if Q dot low is not empty, then I need to insert the low bits into the appropriate second level data structure. Right? And then I'm done. What if Q dot low is empty? Well, if Q dot low is empty, right, it means that that second layer, the block associated with X, has nothing in it. And I don't have a data structure. I don't have a second order data structure for it yet. So I need to create a Van Emde Boas queue for Q dot low of XH. And then I need to insert XL into it. Okay. But I have to do something else. Right? So I've just created a new second level block. So what do I have to do to keep track of that in my data structure?
You have to put XH into Q dot high.
Exactly. I have to note that there is now a block in Q dot low of XH. And I do that by storing the high bits, the index of that second block, into Q dot high. Okay. So that's the whole algorithm for doing an insert, right? Any questions about it?
Wait, just make sure you end up with like log2 of B total layers, right?
You end up with log B total layers. That is correct, right? Let's think about that. Essentially, we are dividing the number of bits by 2 in every recursive step, right? So the number of layers is log B. But remember that B was log C. And so the number of layers that we're talking about is log C, right? And this is the big change by using recursion in both places. I'll say that more about this later, but you essentially end up with a log C depth instead of the logarithmic depth that we were looking at before, the single log. Okay. But now let me ask the important question: how does that decreased depth translate in terms of runtime? Right? So let's talk about the runtime of this data structure. So it's a very simple algorithm. So it appears that we can write down a very simple recurrence, right? We can say, and let me put a question mark here, that the time to insert a b-bit word, well, we do some constant work. And then, well, this subproblem has one recursive call, but this one has two, and that's clearly worse. So it's going to look like this, right? TB over 2, right? So to insert the whole word, we insert the high bits and we insert the low bits, and we do some constant additional work, right? And this is a very straightforward recursion, and it gives us an order B runtime. Okay, so we could say, great, we have log C for insertion. But that's not great because we already had that with the much simpler data structures. It doesn't seem like the double recursion is buying us anything. But in fact, the double recursion is buying us a lot. So there is a crucial insight that lets me argue for a much better recurrence. Okay. So I said that in this else pathway, there are two separate recursions, right? Inserting the low bits and inserting the high bits. But are they really two separate recursions that are just as bad as each other?
One of them is like an empty insert.
Exactly, right? I am inserting XL into an empty queue. Right? So all I have to do is put XL into the min field of that recursive queue. So this insertion is order 1 time. And that means that my actual recurrence is that the time for a b-bit word is order 1 plus just a single difficult recurrence on b over 2 bits. And that has an order log b runtime, which, as I mentioned before, is order log C. So whereas previously our data structures had a log C runtime, now it's log C. That's an exponential improvement. Any questions about that?
You have only checked in the insertion. No.
That is correct. Let's talk about the next operation of deletion. So this is a funny thing about the Van Emde Boas queue. I'm not going to talk about delete min. I'm going to talk about, let's talk about delete min. Okay. So anybody have any questions about how we're going to find the min that we need to delete? Where is it?
Q.min.
It's in the min field. Not very hard, right? We remove it. But now we have to replace q.min with the min of the recursive structure. Right? So how do we find the smallest element in the recursive structure?
It's like the dot min field of the minimum of q dot high.
Exactly. So we look in q dot high dot min, right? What is that going to tell us? What is stored in q dot high dot min?
The first b over 2 bits of the minimum.
Correct. It is an index of the first non-empty block. First non-empty level 2 block, right? And equivalently, it's the high bits of the new min, right? Now, we do have to think about one possible special case, right? If, when we look in q.high.min, it's null, if there's nothing there, what does that tell us? Well, that just means that the recursive structure is empty. Which means we should just set q.min to be null, because now the whole queue is empty. Right? Otherwise, it gives us some high bits, x sub h, right? Which is the index of the first non-empty bucket. So now what should we do?
Go to the next layer.
Yeah, what does that mean, go to the next level? So xh tells us where is the first non-empty bucket. So we can find that in q.low indexed by xh, right? That's the first non-empty block, right? And where are we going to find the smallest element of this block?
Just call delete min on that block, like recursively.
Exactly, right? But let me unpack that a little bit. What we're going to do is, we're going to delete the min from it, and that is going to give us an XL, right? And so now we can set the new q.min to be equal to this concatenation of the high bits we found and the low bits that we found. Okay. But we have to be a little bit careful, right? What can happen if I do a delete min from q.low of xh?
Could also be empty?
Yeah, right. It could, if this previous operation empties q.low of x sub h, what does it mean? It means that I have emptied the block. So what do I need to do? If this block is now empty, if this second level block is now empty, what do I need to do to sort of recover the structure of my data structure?
Delete x high from q.high.
Exactly. There's no longer anything in that block, so I have to delete xh, which is the min, from q.high, right? There's no longer a q at position xh. And I need to, and when I do, once I carry out that delete min, the new value of that, I'll get the new smallest block, the new smallest level 2 block, okay? So any questions about this algorithm for doing delete min? Good. So the obvious question is runtime. Right? And this really parallels insert, right? I mean, this is really just running insert in reverse. We have exactly the same structure that there appears to be a, you know, there's a delete min and then possibly another delete min. So it appears like we're doing two recursive delete mins in order to fulfill our original delete min. But just like in insert, it's not really two delete mins. How come?
Like once again, you only do the second one when the first one had like only one thing in it.
Exactly. This only happens, right? If the first delete min had only one item in it. And if your queue only has one item in it, then the delete min costs constant time because all you do is look inside the min field and you're done. Okay, so just like insert, we have in order log b runtime. Okay.
Wait, it should be log c.
See,
Sorry, log c. Thank you. It's a log b runtime, which is order log c. Any questions?
Why do we have to save the minimum separately?
Great. That's exactly the right question, right? I said this at the beginning. You have to keep the minimum separate. The reason you have to keep the minimum separate is to make this argument that we're making now that only one of your recursions is complicated, right? If you don't have that separate min, it gets a lot harder to say that one of the recursions is going to be on a data structure that only has one item in it. Okay. Now, I mean, it's something of a matter of semantics because, I mean, you don't have to literally call this the separate min field. You could, you know, use an element of the array to store this information. But this is the elegant way to say that you kind of have to pay special attention to the smallest item so that only one of the recursions is expensive. Okay? Great. So the Van Emde Boas queue is amazing. It's exponentially better than all the other data structures. I mean, again, if you think about storing 64-bit words, right, the current machine word size, right? So B is 64, right? And so the Van Emde Boas queue is only going to have 6 layers, right? It's going to take you 6 or 12 or whatever memory accesses to extract any integer from this data structure. So is there any drawback at all to the Van Emde Boas queue? Well, the time is fantastic. Where else might we be worried?
The space.
The space, right? So the drawback here is space, okay? So, you know, if I'm going to use a 64-bit queue, what's the space going to be?
2 to the 64.
It won't necessarily be 2 to the 64. Let's assume that I insert just one item. I mean, obviously, since it can store 64-bit integers, it could grow to 64 bits. But what if I only insert a single item? How much space will actually need to be allocated?
Two to 32.
Exactly. right? We're going to need 2 to the 32 at the top level, and then another 2 to the 32 per item, right? So the Van de Boas queue is super fast, but it takes a gigabyte just to store the integer, just to store one integer. So let's think about that a little bit. What are we using those arrays for? We're using the arrays to do lookups, right? We ask for q.low of xh, right? So for any particular value xh that arises, I need to be able to find the value associated with xh. So I could call xh a key, right? And what we all know is that arrays can map an integer key to a value in one lookup, right? You just use the key as an index into the array, and that tells you the value, right? Or gives you a link, or you can put a linked list hanging off the array if there's more than one thing to store with that key. But the problem now is space. The space is equal to the number of possible keys, right? I mean, obviously you're going to have to use some space per key, but the array is going to have all of these holes where there aren't actually any keys, but you need to allocate the space anyway. So the next thing we're going to ask about is how might we more efficiently store a certain number of items to support these constant time lookups.
Hash maps?
Sorry?
Nothing.
Okay. The answer we're going to explore is what's known as hashing or hash tables.
Excuse me, can I ask a question?
Yes, absolutely.
Could you re-explain the memory part for the...
Yes. So remember that the Van de Boas priority queue at the top level uses an array of pointers to second level priority queues. And the size of this array is square root of C, right? It's letting you index B over 2 bits. So you could also write this as 2 to the B over 2, right?
Yeah.
And so that's our space bound, right? If we want to store keys of value up to C, we have to use root C space.
What is the per item cost you're counting?
Sorry, 1.
No, I mean, why are you counting the per item for the queue? I'm talking about the second.
Oh, this. So, right, because this is assuming that they all land in different level 2 blocks. Right, so if I'm lucky, right, the first item that I insert, I'm going to have to allocate a level 2 block as well. Right, if I'm lucky, the next key will share that level 2 block, but it probably won't. So I'll have to allocate another level 2 block. And so, you know, as I insert more and more items, I'm going to be having more and more of these level 2 blocks.
I see. So shouldn't we count for the arrays of the next layers, because we should allocate them as well?
So this is a lower bound, right? I mean, the fact that the Van de Boas queue is doubly exponential mean that the sub-queues are actually negligible size compared to the top level.
But I think we
structures.
should multiply like a 32 to this memory, because in each layer there is a 2 to the 32 memory.
No,
space.
that's the point, right? So this is going to be a queue on 32-bit integers, so it's only going to need about 2 to the 16 space, which is just nothing compared to the 2 to the 32, to the size of this 2 to the 32 array.
No, but what about the two arrays of the next two? Like.
Oh, you mean the q dot high? Well, yeah, yes. I mean, basically, this is q dot. This is the q dot low array, right? And yes, I will also need a q dot high priority queue, which will require. But again, q dot high is only on 32-bit integers, so it will only require 2 to the 16 space.
I see.
Okay. But again, I wasn't trying to do an exact bound here. I was just giving you a lower bound that you're going to be spending a gigabyte per item. And that's enough to motivate looking for something better, right? So we're now going to start on hashing. And one of the reasons that I like to teach hashing at this point, this, by the way, is the last data structure topic, which we'll finish today or next time. And after that, we're going to be moving into combinatorial optimization and looking at max flow. But I want to spend a little time on hashing because it is our first exposure to randomization in algorithms. And, you know, I stated as a prerequisite of this course that you need some basic probability. And all the probability that you really need to know is going to show up in this lecture or in this topic. It's sort of 5 critical concepts, which I will sort of jot down on the board as I get to them. We're going to use it to implement dictionaries, okay, which allow you to insert, delete, and look up keys. And you can use, I mean, the simpler version of this is sets, where all you're doing is inserting, deleting, and lookup keys. To make it a dictionary, you associate a value with each of these keys. Okay. So I assume that you've all seen hashing before because this is something that is covered in basic algorithms classes. But a lot of the basic algorithms classes make assumptions in order to prove that hashing does well. And I'm going to prove to you how to make hashing work well without any assumptions at all. That's where the randomization is going to play a very important role. So our model is that our keys are integers. Right, this is what we had in the Van Emde Boas queue problem, and I'm going to define the range of those integers to be 1 through m. Sorry for the notation change, but I like to be consistent with sort of the standard texts. So this was previously c. Now we're going to use m, and so as we've discussed, we can store them in an array of size m. But now suppose that we know that we're only going to store n keys. Can we somehow use just n space instead of m? And still get order 1 lookup times and insert and delete. Right? We certainly know how to do small space data structures for lookup, like a binary search tree, for example, only uses n space for n items. But that costs us in lookup time because now we're spending log n time on our inserts and deletes and finds, even if we use splay trees. Okay. So actually, I'm going to ask a more general question. Can we use some other number s of space where S is greater than N in order to store these items and still get fast lookups. And there's a general approach to this where we define some hash function which maps all of our keys, the range 1 to m, into the smaller space of an array of size s, right? And now we can store key k in an array at position h of k, right? And so now this works just like an array, right? When we get a key, we compute the hash function and we look in the array, and that gives us the value for the key. What is the potential problem of using a hash function like this?
You can have, well, you can have multiple items mapped to the same spot. Or
Exactly. You have the problem of what's called a collision. You may have many items being mapped to the same bucket. Now, this does not pose a correctness problem. I can just put a linked list hanging off of the bucket in order to store all of the items that map to the bucket. So no problem of correctness, but why is this still a problem?
Because the linked list could, in worst case, be linear. Fine.
Yes. And what does that, what are the consequences of that?
It's going to be slow to find an item. You're just going to have to go through the linked list.
Exactly. Because the operation time is now going to be proportional to the linked list's length. Right? I mean, you could make it a little better. You could put a binary search tree there instead of a linked list. But if the number of items that lands in a bucket is large, then the access time is going to exceed a constant. Right? So the trick is to come up with a good hash function. Right? One which has few collisions. Okay. So can anybody give me a good hash function?
Well, if the hash function is fixed beforehand, like by pigeonhole principle, you can't.
Exactly. The answer to my question is no, right? There is no good hash function. For all hash functions, there exists a set of keys that collide, a large set of keys that collide. So it seems that we're doomed, right? You know, if the hash function is mapping a large range of values to a small number of buckets, then many of those values end up in the same bucket. And if somebody decides to hand us those values, they're all going to be in the same bucket. And that means that our hash function, our hash table is going to do very slow accesses. Okay. So the solution is to create what's called a hash family. Which is a set of hash functions such that you can pick a good one for any set of items. Make sense? So supposing now that I am allowed to consider more than one hash function, can you give me a strategy that will yield a good hash function, or at least, you know, that we could say it would probably yield a good hash function? Well, we're entering new territory here. What if I pick a random function? Right. That is, I just pick a random value in S for each each input in M. How's that going to do at collisions?
It should do pretty well in that between each pair of elements there is like an n's 1/n chance of collision.
Great. So the intuition is that any two items are unlikely to collide, right? And if any two items are unlikely to collide, it just seems that there won't be that many collisions. Okay. And let's explore that. Let's ask about the average number of collisions with a given item. And to do that, I'm going to have to introduce some of our probability concepts and notation. Okay. So I'm going to write in a variable Cij, which is equal to 1 if items I and j collide, and 0 otherwise. So this is what's known as an indicator variable, right? It's a 0, 1 variable indicating the occurrence of some event. Okay. And now I claim that the time to find I is just equal to 1 plus the sum over j of Cij. Right? No probability in this line, right? Each Cij is 0 or 1. And so the sum of Cij is telling me the number of collisions with I, the size of the linked list that I is in. So now I can say that the expected time to find I is just the expected value of 1 plus the sum over j of Cij. Yes? Okay. How do I evaluate this expectation? Or how do I simplify it?
Linearity.
Right. So I claim this is equal to 1 plus the sum of the expectation of theCij's. And this is the idea of linearity of expectation. And so this is concept number 2. There's 5 of them that I'm going to be hitting, right? And we've already gotten to 2. So we can compute an expectation. We can simplify one using linearity of expectation. Now, what is the expectation of Cij? And I don't mean the quantity, but how do we understand it? What do we understand that to be?
Sum of probabilities times values.
Right. And in this case, the values are 1. So this is simply the probability that j and I collide, summed over all the j's. Yes? Sorry, I just noticed there's a glare on the board. Let me fix that. Next time there's a glare on the board, somebody should yell at me. All right, so we've now simplified in our goal of analyzing this average number of collisions to just computing the probability that I and J collide. Right? When they are randomly assigned values in the range from 1 to S. Okay. Or if you want to be a computer scientist, 0 to S minus 1. So what is that probability?
One over S.
It's 1 over S, right? All right. And the way you can work this out, I mean, it should be intuitive, but what you're doing formally is saying, let's condition on where I is. And now we just need the probability that J takes on a particular value, right? So it's the sum over all possible buckets B of the probability that J goes to B conditioned on I going to B, right? Times the probability that I goes to B. And you can work that out. Conditional probability is another one of the key concepts that I expect that you already know. Okay. And so that means that the expected time is equal to 1 plus the sum over J of 1 over S. And so now we just have to remember that we're talking about n items. And so this is 1 plus n over S. Okay. Any questions about that? So this is great, right? If we just use a random function, then, you know, on average, our lookups will be fast. What's the downside of using a random function?
Have to keep a table for the values.
Yeah, so the problem is, how do we remember a random function? Right? If we're going to use it, we can use it to insert, but then we also have to use it to look up. We can't switch to a different function. How much space does it take to write down a random function that maps from m items to the interval to S positions?
Takes M space.
Takes M space, right? It's actually M log S. Because it turns out that there's nothing better to do than just write down every value of H for all of the possible inputs. Another way to say that is that there's just too many functions. And so the amount of information that you have to record in order to pick one of them is M log S. Okay. So for order 1 search time, we need a function that we can evaluate in order 1 time, right?
Why is the M log S the best thing we can get?
It's basically information theory. How many functions are there that map from the set of M values to the set of S values? There are S to the M such functions. And that means that the number of bits that you have to write down to specify one of them is the log of that.
But why should we? I mean, we don't need to specify the function to remember the values of.
So you're saying that we only need to remember the values of the keys that we actually hashed.
Yes.
That is true, but if you think about it, remembering the values of the keys that we actually hashed is a dictionary problem. So you're saying that if we could solve the dictionary problem, then we would have a solution for the dictionary problem, which is true, but not useful.
But this problem is different because the numbers that we're saving are in the range 1 to S.
Those are the values that we're saving. The keys are in the range 1 to M.
Yes, but I mean, like, if we, maybe if you use a hierarchy and I mean, the things that we are saving are in the range 1 to S compared to the values that.
Well, that's actually that's why there's a log S here, is because we only have to save log S bits per value, but the number of values that we need to save is still large. That is, I mean, again, a dictionary would solve this problem, right? What you're saying is that in order to do this, we need a dictionary that can hold n items that each involve S bits, right?
Yes, but I mean,
That's the problem that we're trying to solve right now, is to make a dictionary that takes n items and stores a value with each one.
Right.
Okay.
Right.
All right, so we need a function that we can compute in order h time. Okay. So this is where we introduce the one probability idea that you may not have seen before. And this is due to Carter and Wegman. Who define this idea of what they call two universal hash families. So why did we think that a random function was a good idea? Well, a random function was nice because it let us do this very simple analysis of the expected number of collisions, right? And show that it was small. Okay. But does the function really have to be random in order to give us a small expected number of collisions? Right? For our collision analysis, we considered pairs of items. Right? We didn't consider the entire collection of items all at once. We were just asking about the probability that I collides with J for every possible pair I and J. So that means that it is sufficient for our function to be what is called pairwise independent. Which is saying that it looks random to each pair of values, even though it might not be a truly random function. Now that is a pretty interesting concept. If you haven't seen it before, you might even ask whether there's any difference. So let me show you a difference. And let's just think about coin flips. Okay, so if I flip 3 coins, X, Y, and Z, right? What can I say about the probability that X comes out the same as Y?
One half.
It's a half, right? This is a collision of the coins, right? There's a quarter probability they're both heads, a quarter probability that they're both tails, right? And the same is true for the probability that X is equal to Z and the probability that Y is equal to Z, right? But suppose I'm lazy, right? And I don't want to flip 3 coins. Suppose that I instead flip 2 coins, X and Y. And then I set Z to be the exclusive OR of X and Y. Okay? So I only flip 2 coins. And so certainly it is still true that the probability that X equals Y is equal to 1/2. But what can I say about the probability that X equals Z?
Also 1/2.
How come?
Because, so you set X, and then depending on the choice of Y, right, it's going to flip either if Y is heads, right, they'll be equal, and if Y is tails, they'll be opposite.
Exactly. I mean, if I think of heads as 1 and tails as 0, this is just equal to the probability that Y is 0, right? Because if I set Y to, if I XOR with a 0, I get the same value. And so that's 1/2. And similarly, the probability that Y is equal to Z is equal to 1/2, right? Because that's the probability that X is 0, right? So you can see what I did here, right? Are these 3 values, X, Y, and Z, independent of each other?
Oh, no.
They're not, right? No, because in fact, Z is equal to the exclusive OR of X and Y. If I know X and Y, then I know Z. So there is no independence, right? And I should have underlined independent the first time I used it, because that is the next of our key probability concepts, right? But any 2 are independent of each other. And this is exactly the notion of pairwise independence. And so to distinguish this from, we talk about mutually independent. When we want to talk about everything being independent, we call it mutual independence. And so X, Y, and Z are not mutually independent, but they are pairwise independent. And so if we were just talking about hashing coins, we could use a pairwise independent function in order to decide where everything goes, okay? And so what Carter and Wedden realized is that you can generalize this, that you can actually make a hash function look pairwise independent when the inputs are coming from a much larger range than 0 or 1. And so next time I'll show you how we do that and how this gives us a constant time hash function that supports lookups and inserts without requiring any additional storage space to represent some big complicated function. Okay? So, are there any questions about that? Okay, so on Friday we will dive into the question of how does one create a pairwise independent hash function, and then fill in the details of using it for fast hashing. And then we'll finish up data structures and start our next topic. So I'll see you on Friday.